In this video, we're going to talk about section 7.3, systems of linear equations in two variables. When we graph two equations of the form ax plus by equals c, there will be two straight lines. Two such equations are called a system of linear equations or a linear system. A solution to the system of linear equations in two variables is an ordered pair that satisfies both equations in the system. We touched on this briefly with an example in class the other day, but let's talk about what this means. So, as we know, if an equation is of the form ax plus by equals c, it is a linear equation. If it is a linear equation, when you graph it, you will get a straight line. So, or a line, as all lines are technically straight. But, so if you graph this, you'll get two straight lines. And so, for example, let's say we graph one of the equations and it looks like this, and we graph the other equation and it looks like this. When you graph two lines, they will intersect in one point. There is a possibility that they will not intersect, in which case they are parallel and they have no solution. So if you have two lines that end up being parallel, they have no point of intersection, so they have no solution. And sometimes you graph a line and it ends up being the same line, in which case, if you graph both your equations and they end up being the same line, then we have an infinite number of solutions, because the points that work for one line will work for the other ones. We'll talk about this a little bit later. So for right now, we're going to look at a system of linear equations and the point where they intersect will give you an ordered pair. So this is some ordered pair, x and y. And if you recall what we've talked about with linear equations, when you have a linear equation, it is made up of an infinite number of points that make the equation, a line is an infinite number of points that make the equation true. So this line right here has an infinite number of points that make its equation true. This line right here has an infinite number of points that make its equation true. And this one point that they share, their point of intersection, is the one point that they have in common. That is their solution. So this point of intersection is the solution to the system of linear equations. Okay, you can find the solution algebraically by using something we call substitution. You can find it graphically by graphing them and finding their point of intersection. So let's take a look. The first problem asks us to determine whether negative 4, 3 is a solution to the following system. So based on what we know that these are both linear equations. If we were to graph these, then they would indeed have a point of intersection because they're not the same line. They're not parallel. So they would have a point of intersection, and the question is this that point of intersection? So the point of intersection, if you recall, is the one point that works for both equations. So to see if this is a solution to the system, we simply need to substitute this in for x and this in for y in each equation. So I'm going to substitute in negative 4 plus 3, or excuse me, plus 2 times 3, and my question is, does this equal to 2? Negative 4, 2 times 3 is 6, and this does equal to 2, so negative 4, 3 is a solution to this equation. It has to be a solution to both equations in order for it to be a solution to the system. So we could subtract, and then 2 times 3, and the question is, does this equal to 6? And when we substitute, this is going to be negative 4 minus 6. And the question is, does this equal to 6? And this is negative 10, which does not equal to 6. So therefore, this is negative 4, 3 is not a solution to the system, because it works in one of the equations but not the other. So it's a point on one of the lines, but it is not a point in both of these. So it is not a solution to the system. Okay, so let's talk about how we can find solutions to the systems. So solving a system of linear equations. So when you solve a system of linear equation, really all you're doing is you're finding that point of intersection. So if you have two lines that cross right here. This is an ordered pair sum x, y, that when you substitute it into your each linear equation, it should make them both true. This is a point that works for both equations. In this problem, we're being asked to solve a system of linear equations by graphing. So, as we've talked about in the previous videos, we can graph each of these equations by finding our x and y intercept. We can graph these equations by creating a table and plotting our points. We can graph these by putting it in slope-intercept form and using that to graph using our slope and our y-intercept. I think I'm going to do that just for practice. So if we take this first equation, 2x plus 3y is 6, and we solve for y, because remember we want it in this form, y equals to mx plus b, because once it's in this form, we've got our slope and our y-intercept. So I'm going to subtract 2x from both sides. And when I do that, I'm going to get 3y equals negative 2x plus 6. Divide each term by 3. And I got y is negative 2/3 x plus 2. So for this first equation, your slope is negative 2/3. And your y-intercept is 2. With the second equation, I have, let's see, 2x plus y equals negative 2. Subtract 2x because I want to isolate the y, and when I do that I get y equals negative 2x minus 2, and in this problem your slope is negative 2, which we'd write over negative 2 over 1 as a ratio, and your y-intercept is negative 2. Alright, so let's graph this second equation. Your y-intercept is negative 2, so we know we have a point at negative 2. And your slope is down to right 1. So from here, I'm going to go down to right 1. And that gives me my 2 points on that line. Okay? Now, if I want to come back in here, and I'm going to graph this equation, the slope here, the y-intercept in this problem was 2. And so here's my y-intercept, which is 2. And my slope is down to right 3. So I can go down to 1 to right 3. And when I do that, I have a point here. So again, I have no explanation for this. So I can draw this. It's going to go through like this. And if I extend my other line, it was here. Sorry, it's here. Is that right? One should be going through here. I'm not really sure what to do here. Up right 1. And so my graph actually should be going through here, and that point of intersection is going to be 1, 2, 3, negative 3, and 1, 2, 3, 4. And I apologize for my pen acting up. I'm not really sure what's going on. All I was doing here was trying to make sure that I got this graph, and so I used my slope, which was down 2, right 1, down 2, right 1, down 2, right 1, and I was able to find those points, and I was able to find my point of intersection. What you can do here is do this on graph paper and then use a straight edge, or you can go in and use your graphing calculator, and I apologize for my messy screen here, but you can go in and use your graphing calculator. And let's go back to that problem there. So we go in here and we go back to our y equals, and we can type in our equation now that they're in slope-intercept form. My first equation is going to be y equals to negative 2/3, so make sure you use your negative 2/3, so 2 divided by 3. And actually, since this is a fraction, I'm going to put it in parentheses. So this is going to be negative 2 divided by 3, close parentheses, x plus 2. Whoops. What's going on there? I'm not having much luck with technology right now. So let's clear that out. So this is going to be negative 2 divided by 3, close parentheses, x plus 2. And then my second equation is going to be negative 2x minus 2. And I'm going to go to my window, which is this button to the right of the y equals 2. And my window is in standard negative 10, 10, 1, negative 10, 10. If it's not, you can just use your down arrow, or as we talked about in class the other day, you can go to Z standard, which is 6, and when you click on that, it gives you a standard viewing window, and you can now see your graph. And they even use the same colors that I did. That was not intentional, but you can see the point of intersection is up here. We found the point of intersection to be negative 1, 2, 3, so negative 3 up 4. So we can find that, we can calculate that intersection. We talked about this in class. You can go to second, calculate, which is this button right here. You can go to intersection, which is number 5. They ask if this is your first curve, if this is your second curve. You get a chance to guess if you want. And then you can find your point of intersection, which is negative 3, 4, which that is the point of intersection that we found. So the solution to this system of equations is indeed negative 3, 4. So let me see if I can pull that back up. Okay, so our solution is negative 3, 4. And I'm actually going to provide a couple of links to some videos that I've done before on using your graphing calculator to solve these. So if you didn't quite get that, you can always rewind this video, or you can look at the link that I will be posting. Okay, so that's solving systems of linear equations graphically. Let's solve them algebraically. There are two ways to solve systems of linear equations algebraically. One is the substitution method. The other is the elimination or the addition method. So when you solve a linear system by substitution, and this can be found on page 435 of your textbook, you solve either of the equations for one variable in terms of the other. If one of the equations is already in this form, you can skip this step. The second step is to substitute the expression found in step 1 into the other equation. This will result in an equation of one variable. Solve the equation, and then back substitute, and then check your solution. You can always check your solution. I should have mentioned that in this previous problem. If you want to confirm that negative 3, 4 is the solution to the system, you would substitute it into this first equation and the second one and make sure it's true for both. Okay, so this is a little bit much, so let's go ahead and just look at an example. So I'm going to take this same problem that we had, and I'm going to solve this by the substitution method. So with the substitution method, literally what you're doing is you're taking one of these equations, solving for a variable, and then substituting that equation back into the other equation. When the substitution method works the best is if you have a variable that has a coefficient of 1. If it's already solved for that variable, it's even better. So I'm going to take this equation right here, 2x plus y equals negative 2. And I'm going to solve for that y. So I can solve for that y by isolating the variable. And when I do that, I get y equals to negative 2x minus 2. Now, once you know what y is equal to, you can actually substitute this into the second equation for y. So what I did was I took one equation, solved for a variable, and then I substituted it in for that variable in the previous equation. If you substitute it back into the same equation, everything will just cancel out. Alright, so here I'm going to substitute this back in, so I'm going to have 2x plus 3, but instead of y, I'm going to put my new expression, negative 2x minus 2, which I got from the second equation. And then when I do that, this is going to give me, so I substitute it in here, equals to 6. And now this is what the previous thing was talking about, the previous explanation when it says substitute the expression into the other equation. This will result in an equation in one variable. So now if you look, the only variable here is x. So now this is just a linear equation in one variable, which you guys know how to do. So we can clean this up. We can distribute. And when we do that, we get 2x minus 6x minus 6 equals 6. Combine like terms, this is going to give me a negative 4x minus 6 is 6. Going to isolate that variable, that x, by adding 6 to both sides. I get negative 4x is 12. Divide both sides by negative 4. And x is negative 3. So I've got part of it, so I've got the negative 3 for x, and I can take this and substitute it back into either equation, and you always want to go back to one of the original equations. I'll substitute it into the first. So I'm going to substitute a negative 3 there, plus 3y, and I'm going to solve for y. So equals to 6. That's going to give me negative 6 plus 3y is 6. Add 6, and when I do that, I'm going to get 3y is 12. Divide both sides by 3, and y is 4, giving me order paired negative 3, 4. So you can check this by substituting it back into both equations to make sure it holds true. But if you recall, this is the same problem we just did graphically, and we were able to get the same answer by finding simply their point of intersection. So far, I would say I'm pretty convinced that this is indeed the correct answer. So we found it by graphing, in which case we looked for the point of intersection. We found it by substitution, in which case we manipulated one of the equations so that it was set to equal y equals there. This is a little misleading here. Let me do that. So separate here. I'm just going to do it that way. So we solved for y here, and then we took this and we substituted it back into the other equation, and then that gave us our, so this was our step 1. We substituted it back in. This was our step 2. And then we solved that, and we found x is negative 3, and then I plugged that in back in to solve for y, and that gave me the ordered pair negative 3, 4. Okay, now we can also solve this by the addition method. This is often called the elimination method as well. So step 1, if necessary, rewrite both equations in the form ax plus by equals to c. And then, if necessary, multiply either equation or both equations by appropriate non-zero numbers so that the sum of the x coefficients or the sum of the y coefficients is 0. Add them, solve the equation, back substitute. And that back substitute part is the same thing we did in the previous problem. Okay, let's just look at an example. I think it makes more sense that way. So I'm sticking with this same problem. So in this problem we have 2x plus 3y equals to 6, and 2x plus y equals to negative 2. So what you want to do with these problems is you actually want to be able to add your x terms or your y terms and make one of those terms cancel out. Now if I added my x terms, I would get 2x plus 2x, which would give me 4x. If I added my y terms, I'd get 3y plus y, which is 4y. And so neither of my variable terms cancel out. So what I could do is I could multiply one of these terms by a negative 1. And if I did that, so let's see what happens if I multiply by a negative 1. If I multiply this by a negative 1, my new equation becomes negative 2x minus 3y equals negative 6. And notice I distributed it to each term there. And I'm going to leave this bottom equation the same. Sometimes you have to convert both of these, but in this case we don't need to because it works out this way very nicely. Sorry about that. So here all I did was I multiplied, and because of your properties of addition, for property of equality for addition says if you do something to one side and do it to the other, in this case it would be multiplication. As long as we multiplied every term by that value, our equation will stay the same. Now, why did I choose -1? Because -1 times 2 gave me a -2, and now when I add a -2x and a positive 2x, I get 0, and that was the goal, was for one variable term to cancel out. So a -3y and a positive 1y is going to give me a -2y. -6 minus 2 is going to give me a -8. And now you just solve. Divide both sides by a -2, and y is going to be a positive 4. Once you solve for y, you have to substitute back into either equation. So I'm going to come over here and do that. I'll substitute back into the first to solve for x. So I can use that, and equals to 6. This gives me 2x plus 12 equals to 6. Subtract 12. I get 2x is -6. Divide by 2, and x is -3. And again, I have the ordered pair -3, 4. Now, you can see that we did this problem graphically by drawing our lines, plotting our lines on the graph. We did this using substitution, we did this using elimination, and all three of these work. As you start to work more of these problems, you'll realize that sometimes substitution makes more sense, sometimes elimination makes more sense. For this problem, substitution was pretty straightforward because it was easy to solve for the y, but elimination, or the addition method, also made sense because it was pretty easy to manipulate this 2 to be a -2, and those terms can cancel out. All right. I'm going to post these notes in Moodle so that you can actually get to these links, but these 3 links will take you to 3 more videos that I've made previously for other classes with more examples of solving a system of linear equations graphically. And actually here I talk more about the graphing calculator, solving a system of equations using substitution, and solving a system of linear equation using the addition or the elimination method. The next video that I'm going to do is actually going to be some applications with these systems of linear equations, so be sure to check that out as well before you get to work on your lab. I hope that helps. If you have any questions, please let me know.